Okay, so one second. Can you see my screen?
Yes, ma'am.
Yes,
Okay,
ma'am. Hello.
yeah. So today we'll be discussing week 9. And before starting with week 9, let's first talk about one second. Can you see the screen? You can see the
Yes,
screen,
ma'am.
right? Just one
Yes.
second. Okay. So how was your quiz 2 exam? How did you guys
Ma'am,
find it? Yeah.
ma'am, it was good. I did not do any wrong answer there. I just missed some correct answers basically in the MSQ type questions.
Okay, so obviously you'll have your marks deducted a little, but that's fine.
And
So
ma'am, there was a question regarding the projection of a vector where we have to basically write the sum of the coordinates.
yeah.
And I did the answer 16.44, but in the answer key it is given 16.3 to 16.44. So will I get the marks?
Yeah, you'll get the marks. 16.44 is in the interval, right? So
Okay.
most likely you're going to get marks for it. Okay.
Okay.
And what about others?
It was good, ma'am.
Okay, so I hope the paper was easy. And
Ma'am,
yeah,
I have a doubt. I have asked in chat box. Can you please encounter that?
a doubt regarding, okay, if a matrix is given, how we can find that an arbitrary vector belongs to the column space of A or not. So for you to check whether an arbitrary vector or a vector belongs to a particular vector belongs to the column space of a matrix or not, you just have to find if there is just one second. What you have to do is, let's say you have A and you have to find whether X or V is in the column space or not. So what you have to do is you have to find a vector Y. Let's say this is an M cross N matrix. So you have to find a vector Y such that A multiplied with Y should give you V. If that's true, that means V is in the column space of A, right? We discussed it in sessions, I guess. How do we check whether a vector is in the column space or not? How do we check whether it's in the row space or not? Do you guys remember? We have discussed this thing in class. Okay. So it's fine now, right? You put v equals to whatever the vector is given to you, put that here and try to find whether there's a y or not. So basically, you just have to find whether y is in the, yeah, that's how you find whether y is in the columns. It's the augmented part that you have to do, this one. You have to solve this and see if it has a solution or not. Is that okay?
Yes, ma'am.
Okay. So we'll discuss if anyone has any doubts in the question paper. So we'll discuss those doubts towards the end of this session. And for now, we'll start the summary of week 9. So for week 9, the first thing that we have is so we're starting from, okay, so we'll start with a one variable function, and you have dealt with variable functions in maths 1, right? So a one variable function is when you have a function from R to R. So this is called, and we'll only be discussing real valued functions. So real valued functions is what we'll discuss in maths 2 as well. Real valued function means your function is from a domain to R, and that domain is, so real valued means its values are real, right? So they'll come from here. So your codomain should be real numbers. That's the meaning of real valued function. In our syllabus, we'll only talk about real valued functions. So one variable function is, first is a one variable function. One variable function is a function from R to, you can have an Rm here. That's fine. This is also a one variable function, right? One variable means it involves only one variable. So you can have fx is equals to x plus 1, and x minus 1. This is from R to R3, but it's a one variable function because it only involves it only involves one variable. Okay, so that's your one variable function. Then second is your scalar valued function, where you have scalar valued means your function will take scalar values. That means your function is from Rm to R. That means this time your codomain is a real number. Your the values your function can take is real numbers only. It can only take scalar values. That's a scalar valued function. And for example, you can have an example here as f of let's say xy is equals to x plus y. Now this is a scalar valued function, right? Because you'll only get a scalar here. If I'll take the value of f1 comma 2, I'll get 3, which is just a scalar. This is a scalar, and if I'll have something like this is a vector, right? Those are called scalar valued functions. Then next up we have vector valued functions, where your values of your function can take values as vectors as well, right? So vector valued is where function's value can be a vector. That means your function this time will be from Rm to Rn. So you can take f of x1, x2, because it depends on m variables this time, because the domain is this. That means it's a vector from Rm. So it will have m tuples here. And in the codomain part, you will have n tuples. That means it can be x1, or you can just have 1, 2, 3 till n, right? That's also fine. Let's take a simple example here. So I'm taking an example involving three variables only. So I'm taking this to be x1, x2 plus x3 and x2 square. This is also fine, right? Because we're only talking about functions. So your linear transformations can be a vector valued function, right? Depends on the linear transformation. If you're taking a linear transformation from Rm to Rn, a linear transformation from Rm to Rn in general is a function from Rm to Rn, right? That means it's a vector valued function. But if you take your linear transformation from R to Rn, or from Rm to R, then it's obviously a linear transformation. It's still a linear transformation, but it's a scalar valued function this time, right? So this is also a type, this is also one example of vector valued function. And the fourth, then we have multivariable function, where let's say you have a function from multivariable means it involves more than one variable. That's the meaning. So let's have one more example of, this is example one, and this is example two. Let's have an example here where I'm taking x. So fx is equals to, so the problem with, okay, one thing that I didn't mention is, for a scalar valued function here, you should have one. You cannot have anything else. For a vector valued function, yeah, vector valued function, if even if you have one here, that's also a vector valued function. So Rm to R1 is also a vector valued function. Rm to R10 is also a vector valued function. All of it is fine. Then you can also have something like this here, where you take fx, and here you'll have 2x, x square, and x cube. This is also a vector valued function. Then we're having multivariable functions where you have more than one variable, right? More than one variable involved. That means your function is from, because it's multivariable, so we're assuming that the variable number of variables is more than one, right? So it will be, let's say, from Rn, where n is strictly greater than 1, to, or it doesn't have to be, when I write Rn here or something like that here, you just need to have a domain from here, right? That means a domain should be a part of this Rm. That's what we mean. When I write Rm here, I mean there is a domain. The domain has to be in Rm. When I write Rm here, I mean there is a domain. The domain of this function is in Rm. When I write R here, I mean the domain of the function is in R, right? And then here the domain will be in Rn, and this is a function, multivariable function. So it doesn't matter what you take here, but this n matters. So n should be greater than 1. And you can take R here, just R1, or you can take any Rm in general. That's fine. So no restriction as such on m, but we have a restriction on this n here. It should be greater than 1. So you can take an example here where we'll take fx1, x2 is equals to x1 square plus, let's say this one, x2 square. This is a multivariable function, right? Multivariable scalar valued function. It's a multivariable function and it's scalar valued as well. This one will be, if I'll take this, x2 is equals to x1 square and 2x2. And this will be, again, will be a multivariable function, but this time it's vector valued, right? And in case anyone has a doubt anywhere in the session, when we'll continue with the session, you can unmute yourself and ask. If you find the pace too fast or anything, you can
So,
that,
ma'am,
ask those things. Yeah,
function and transformation are same. Question is,
can't hear you clearly.
hello.
Yeah,
Yeah, so function and linear transformation are considered as the same or different.
functions and linear transformations are different, right? What's the definition of function? A function from a domain, domain could be anywhere, and to its codomain. So a function is basically, it has to satisfy only two properties. One is that every element in D should have an image, and every element should have a unique, no two, no one element should have two images, right? So every element should have a unique image. That's the idea, right? If this is your domain, this is your codomain, then the idea for a function is that if you have these points here, let's say if you have these 5 points here, then all of these 5 points in the domain should have an image here. That's the first condition for a function. The second one is that no point should have two images, right? This should not happen for your function. That's it. Those are the condition for functions. But when you take a linear transformation has an extra condition which says that it's a function from Rn to R, or not even from from Rn to Rm. Those are the kind of vector spaces you're dealing with. But it's a function from a vector space to another vector space, where there's an added condition where you take x plus y, the image of x plus y. That means the image of the sum of two elements should be equal to the sum of the image of those two elements, right? This is the first condition that should be satisfied. So it should be a linear transformation. First is it should be a function, should be a function. And then second is this kind of function where fx plus y is equals to fx plus fy, and fcx is equals to cfx, right? Is that okay? Where this plus is the sum, is the vector addition in this vector space, and this plus is the vector addition in this vector space.
So the
For
linear
example,
are
yeah, a
always
linear transformation is always a function. Function is not always a linear transformation. You can have a counter example here. So the example here would be, let's take a function fx is equals to x square and x. Do you think this is a linear transformation? Or let's not complicate things. Let's have this. Do you think this is a linear transformation? It's a function from R to R2, right? but it's not a linear transformation. Is that okay?
Yes, ma'am.
Yes.
Then we'll see some examples, and in our syllabus we'll denote so these kind of vectors, because we'll be dealing with vectors here. So we'll denote these things instead of writing this entire thing. We'll just be denoting this thing like this, x tilde. So let's have some examples here. If you have, let's say, if you have a linear function that will be fx plus y. So this one is linear, and this is 2x plus 3y. These are all scalar functions. So we are doing example of scalar ones. And in the example of scalar functions, this is a scalar function, right? Because this entire thing, it always belongs to R. It only has one tuple, so it belongs to R, right? So that means this is a scalar valued function. Then let's say you have fxy is equals to 2x cube minus 2yx. This is another example of a scalar valued function. This is also a scalar, right? If you'll put the value of x and y here, you'll get a scalar number. You'll just get a number here. Scalar means you'll just get a number here. That's it. That won't be a vector. This is also called a polynomial in xy, right? Polynomial in two variables, x and y. Then for the exponential ones, you can take fxy is equals to sine x square plus y square. This is also a scalar valued function. In trigonometric functions category. Then you can take fxy is equals to e to the power, let's take x plus or x minus y square. Let's take x minus y square. We can take this, right? So this is a scalar number. If I'll put the value of x, let's say the value of x is 1 and the value of y is, let's say 0. That means you will have e to the power 1 minus 0. And this thing will be e to the power 1, which is a scalar number, right? It's not a vector. So that means this is a scalar valued function in exponential form. So exponential functions as scalar valued functions, then we have, and obviously all of these are multivariables, right? So these are scalar valued functions, but with them, they are also multivariable. Scalar valued multivariable functions. So, and then this one is a little different. This one does not come under this category. And if we have to discuss, let's say, some other example, let's take one another example of, and you will tell me what kind of function this is. 2x plus 3y e to the power minus x square plus y and sine xy square. What kind of function is this?
Vector by two multivariable.
Right. So it's a vector valued function first thing, because the values here on the codomain side are vectors. That means it's a vector valued function. And then it is multivariable because it's involving more than one variable here. It's a multivariable function. Let's have an example. F x y z equals to, let's say you have x y z sine y cos x y. I just want you guys to be familiar with the kind of functions that we'll be seeing. Not exactly these kind of complicated functions. This one for x, y, z greater than equals to x, y, and z. All of these greater than equals to 0. And here let's take x, y, z, sine z, cos z, and e to the power y square. Otherwise or else. So what kind of function is this? This means if your x, y, z takes value greater than, that means if your x, y, z, all of these three variables are greater than 0, for that your function is this. So firstly, it's a again, it's a multivariable function, it's vector valued, right? This is a vector, this is also a vector. So first is that thing. And then the second one is that it's a branch function. That means it is divided into two parts. One is when your x, y, z, all of these things are greater than 0, your function takes this value. Let's say your x's value is x is 0, y is 10, and z is also 10. Then you'll have this thing will be sine 10. Here you'll have 0 because all of these things are greater than equals to 0, right? Your x, the value of x, y, z, all of them are greater than 0. That means I should be considering this part, right? Not this one. So I should be substituting x equals to 0, y equals to 10, and z equals to 10 here in this part of the function. Because for these values, this part of the function is valid, right? So what will I get for these x, y, z? I'll get 0. Then here if I'll put x equals to 0, I'll get cos 0 is equals to 1 and sine 0 is equals to 0. So at this point, I'll get this value. Let's say if I have y equals to, let's say if I have x equals to 0, y is equals to minus 10, and z is equals to 10 again. Now this time, since all of these numbers x, y, z are not greater than 0, that's why I should be considering this part of the function, right? So I should be putting x equals to 0, y equals to minus 10, and z equals to 10 here in this function. So this will give me 0 here, then cos 10, and then we'll have, here we have e to the power y square. So that means e to the power 100, right? So this will be my function's value at this point. If this is the point, then the value is this. If this is the point, then the value is this. I can just write f here. F of this is equals to this, and f of this point is equals to this. So we have discussed all kind of functions that we might see in multivariable calculus. And then we can move to the operations, the arithmetic operations that we can perform on these functions, right? So operations, the basic ones, addition, subtraction, and all. Let's say if I want to have a function f and if there's a function g, let's say there are two functions. If I want to add these two functions, then for me to be able to add these functions, what should be true? What should be true about the domain of f and domain of g and domain and the codomain of f and codomain of g? Are there any restrictions on these two? Let's say if I have, let's say if I have fx is equals to, or let's say if I have fx plus y is equals to x, and the other function, let's say g is gx plus y is equals to, not even this one, x comma y, and this thing g x comma y is, let's say x plus y comma x. Now can I find the sum of these two functions? Do you think we can construct a valid addition for these two functions? Can we define addition for these two functions? If I'll add, let's say if I have f plus g, let's just take x here. To make things simpler, I'm just taking x here, and here I'm taking x and this thing. Can you see it now? Can I add these two functions? You have studied the sum of two functions, right? Two one variable functions in Maths 1. How do we define the sum of two one variable functions? So if you have one variable functions, we used to define this as fx plus gx, right? Where we'll first find the value of f at x, then we'll find the value of g at x, and then we'll add those two values. So that means if I want the sum of these two functions to be defined, then my codomain part, this part, the range part, or I should say codomain, should be of the same dimension, right? If this is one dimensional, can I add a one dimensional vector to a two-dimensional vector? For me to be able to do this thing, I need to add this one dimensional vector to this two dimensional vector, which is impossible. That's why the sum will not be possible here. That means your codomain should have the same dimension, right? That means if I'm taking this function from something from a domain to Rm, then this function also, this function g function 2 should be from some domain to Rm. And same goes for domain, because my domain has to be common for both, right? If I'm defining, so this will be from Rn to Rn only. So if you want to add two vectors, two functions, who's on unmute? Okay, so if I want to define the sum of two functions, then I need to, first thing that I need to make sure is that the domain of both of these functions should be same, and the codomain of both of these functions should be same as well, right? Range need not be same. I want the domain and codomain to be same for both the functions if I want to add them. Range might differ, and that's fine. So f plus g of, let's say you're taking x tilde, because we've already seen that if you'll take a number, if you'll take one element from Rn, it will look like x1 to xn, right? And we call this thing as x tilde for simplicity. So we're calling this entire vector x1 to xn as x tilde. So this thing should be equal to, it's simply just fx tilde and gx tilde. And I want the domain. For the sum to be defined, the domain and codomain should be same. The domain of this should match with the domain of this, and the codomain of this should match with the codomain of this. And the same goes for subtraction as well. So it's the same for
Ma'am,
subtraction. Yeah.
you said that the domain, that is Rn, you were defining all the elements in the domain as f tilde, right, and g tilde.
No, the elements here from Rn, your domain is in Rn. So that's why, because every element in Rn looks like this, right? So these type of elements, I am, instead of writing this entire thing, let's just write this as this, x tilde, that's it.
Okay, ma'am. Yeah, got it.
Same applies for the subtraction part of two functions. So for subtraction as well, the domain, the same rule applies as the one for sum. Then coming to the multiplication part, if I want to define the multiplication of two functions, and this is different from this. For the multiplication part, because again the same rule goes here, right? Because you'll have, let's say you're doing fg. Then do we know how to, first thing is, if you'll have fg, then the domain, because we define this as fg, even in one variable functions, we used to define this as fg of fgx as fx into gx, right? In one variable functions, we used to do this thing. Now, if we're dealing with multivariable functions, then we'll have fg x tilde here. So first thing would be that your domain, again, because you're using the same element for both of these, x and x here. That's why the domain of both f and g should be same. So if you want to multiply two functions, the domain should be same, right? Rn to something, and G is also from the domain that's in Rn to something, right? Both of these domains should be same. And what about the codomain part? If I want to multiply two things, can I have a vector here? Can I have a vector valued function? Let's say if I have 1, 2, 3, and unless I don't define the product in a specific way. Let's say if I'm defining the product to be the dot product, then that's a different thing. But if I don't know how to define it, then I'd need both the functions to be scalar valued, right? Because
Yes,
okay, this
Naveen.
has to be a scalar valued function. We don't have to get into the detail, but this thing has to be a scalar valued function. This also has to be a scalar valued function for us to be able to define the multiplication thing. That how do we define them? 2 and 3 is a defined multiplication, whereas if I take 2 1 and 1 3 and someone just asks me to multiply these two things, I don't know what that means, right? So for that reason, we just take scalar valued functions here, and same applies for the division part as well. So for the division as well, you would need same rule goes here. So if you take f by g, so our rule is the same here. This is fx tilde and gx tilde. So if you want to take an example, you can take, let's take this thing where you have f and g, both of these from R3 to R, let's say, or R2 to R, let's take. And I'm defining the function f as fxy as x plus y and gxy as x minus y. Then I can define the product of these two. The product then will be fg of x comma y will be equal to f of x comma y multiplied with g of x comma y. This thing is x plus y. This other thing is x minus y. So this is the function. This is how the product is defined. Then coming to the division part, if you have f by g, and if you are using it on x tilde, then this will be fx tilde and gx tilde. So you can do the same thing for this one, right? If I take the same thing here, I'll have, and we don't know how to divide. If I have 1 by, do we know how to divide these two things? This does not even mean anything, right? If I'll define this, do we know how to divide 1 comma 2 by 2 comma 3? That's not a thing that we have studied so far, and we don't define division between tuples, right? So that's why these two should be scalar values. Let's take this example here. So if I have f by g of x comma y, this will be equal to f x comma y by g x comma y, right? And this is x plus y by x minus y. This is how you define division. Then we have the composition part where we have FOG. Now, if I want to define FOG, then first thing that I'll need is let's say if I'm taking the domain of, let's come to G first, because F is decided later, right? We first apply G and then we apply F. So we should start with G. So if the domain of G, let's say, is D, and it's from D to Rm, let's say, D could be anywhere in Rn, Rm, anywhere. So let's take it to be in Rn. And then if I have to define f, and for me to be able to uh, for for this to be valid, for FOG to be valid, what should be the domain of f? And this can be anything. This is just fine. You can take RK here. That's fine. But what should be the domain here? If I want to apply G to something and that x tilde is coming from D, then this goes the same as we do for one variable functions. The domain of f obviously should be included in the range of G, right? So sorry, the range of G should be included in domain of F. Your range of G, if I want to apply F to this function, fgx, then I need to make sure that the range of G is included in the domain of F, right? That means your range of G should be contained in domain of F. So your domain of F should be something that contains D, right? Not D, contains this range of G. So we can do one example here on composition. Let's take fx is equals to sin x and gx is equals to mod of x square. Can I define FOG here? FOG is not always defined because if you have not chosen the right domain for F for the outer function, then it's not defined, right? I hope you get this thing that if your domain of F, the domain of outer function is not defined in such a manner that it contains the range of G, then your composition will not be valid. So will we have a valid composition here? Let's see. This is a simple one variable function. This isn't even multivariable. Can someone answer this one? Is FOG a valid composition here? You just,
Uh, yeah, ma'am. It can be minus sin x and sin x both.
yeah. So if I'll try to compose G with F, so this
And
will
you
give
have to
me,
specify the domain also. Only then it can be a very like a proper function.
yeah. So let's say if I'm defining the domain F, we're taking the natural domain for both of these functions. What is the domain for this function F? It's R, right? R to
Yeah, ma'am.
minus 1 comma 1. And this one is G is a function from R to R plus union 0, right?
Yeah, ma'am.
So if I were to define FOG, this will be, so first thing we need to check is that the domain of G, range of G. So your range of G is R plus union 0, and this should be contained in the domain of F, which is R. So this is contained in R, so we don't have an issue here. That's fine. Wait, this thing will be, I shouldn't be taking FOG, I should instead be taking GOF. So what about GOF? Is GOF valid here? On the natural domain of F and G, do you think GOF is valid? The domain of F is this. If it is valid, then it will be a function from R. Your GOF, then G or FOG is a function from FOG, then is a function from the domain of G, which is D, to this one, RK, right? So if we have to take this thing, GOF, then it should be from the domain of F, from the inner function, the domain of the inner function, this R, to the codomain of G, which is R plus union 0, right? If it is valid. Now let's see if it's valid or not. My F is, for the validity, I just need that the range of F should be contained in domain of G, right? Range of this inner function should be contained in the domain of the outer function. Is it true? Let's see. The range of F is, this is F function. The range is minus 1 to 1. And what's the domain of G is R, right? No, range is minus 1 to 1. And then your domain of G is R. So we just have to check whether range of f is contained in domain of G or not, which it is, right? Range of f is contained in domain of G. That means your composition is valid. This implies GOF is valid. We don't have an issue here. From R to R plus union 0. And what will be the function? GOF will be equal to, first you have to take G, you have to apply G to f function, which is sine x. That means you have to apply G, which is square root of x square to sine x. So this will be square root of sine square x. And what's the value of square root of sine square x? It's mod of sine x. Whenever you have square root of k square, this thing is mod k, right? So square root of sine square
Yeah,
x
ma'am.
will be equal to mod of sine x. And let's say if I'll change things here, let's say if I want to take, if instead I'm taking, this time I'm taking fx is equals to sine x and gx is equals to square root of x. Now I want to do GOF. Then for the composition to be valid, I want same thing, range of f, the inner function, this one, the function that gets applied first. This function, the range of this function should be contained in the domain of the second function. So let's see if it is true. So for this one, the range of f is, again, the range of this is -1 to 1. And what's the domain of G this time? So your G is square root of x and square root of x. The domain for square root of x is 0 to infinity, right? And this time it's not contained in this. If you take this thing, RF is not contained in domain of G. That means your composition, if you're taking f from R to -1, 1, and if you're taking G from its natural domain, which is R plus union 0 to R plus union 0. If I'm taking this thing, the natural domain of f and natural domain of G, then GOF is not valid. This is not defined or not possible, whatever you want to call it, because the range of f is not contained in the domain of G. Now, can I do something? Can I alter the range or something here such that this composition becomes valid? I want this composition to be valid by altering the range and domain of f and G. Range, domain, codomain. Do you think we can alter something here to make this composition valid? I want this thing, square root of sine x. That's the composition, right? I want this thing to be valid, but my only problem is that sine x does take negative values. That's the problem. That's why this composition is not valid. So can this composition be valid somewhere? Do you think this function is valid somewhere? In some
Yeah, ma'am.
domains, this function will be valid, right? Where sin x takes positive values. If we take this function from domain where sin x domain is x such that sin x takes positive value or zero value to R, then this is valid. This is a valid function, right? It's fine. So, and the domain of composition depends on this thing, right? Domain of composition is the same as domain of the first function. That means I need to, this first function, this is the first function here. So I need to alter the domain of this one. So if I'll take fx, where is your sin x positive, by the way? The sin x looks like this. So for this composition to be valid, let me just write this thing here. For
Ma'am, first
GOF,
and second quadrant only.
okay, let's see, to be a valid composition, we want range of sin x to be contained in domain of G, right? And domain of G is R plus union 0. This is domain of G. Domain of G is equals to this. And range of sin x is, so I need, that means, that is, I want the range of sin x to be greater than 0, right? That means I want x such that sin x is greater than 0 or equals to 0. Equals to 0 is also fine because we don't have a problem here. If sin x takes 0 value, that's also fine. Square root of 0 is a valid thing. So sin x looks like this. And this is 2 pi, this is pi, this is pi by 2, and this is 3 pi by 2, right? And on the negative side, we have the same cycle. This will be minus pi, this will be minus 2 pi. Now, where do you think is sign positive? Sign is positive here, right? From 0 to this thing, 0 to pi. If I were to define the domain of f such that GOF is valid, so I should define the domain of f as 0 to 0 is also fine, pi is also fine. 0 to pi, then I can take 2 pi to 3 pi, right? This is 3 pi. Here also we have the value of sign positive, right? Sign takes positive values in 0 to pi, then 2 pi to 3 pi, then from here to here, this one. Here it takes positive value, then here it takes positive value, here it takes positive value, here it takes positive value, right? So it should be 0 to pi, 2 pi to 3 pi, and it keeps going on. It's not stopping anywhere, right? So that means you should define the domain of f as, for only the positive part, it should be 2n pi to 2n plus 1 pi, right? Odd multiple of pi to even multiple of pi to odd multiple of pi, right? And union here, n varying from 0 to infinity. This is only for the positive part. We also have the negative one here, which says you'll have to take union minus pi to minus 2 pi. Then you'll have to take minus 3 pi to minus 4 pi. So that also needs to be included, right? So for this part, you'll have GOF valid. If I'll take the domain of sin x to be these things, to be the red marked ones, this one, these ones, if that's the domain of your function f, then that means GOF is a valid function. You can define that. Is that okay? Can we move to the next thing?
Yeah, ma'am.
Okay. So the next thing is a curve in Rm. And a curve in Rm is basically the range of, let's say you have a function f. So a curve is a function f from D, which is a subset of R. So that means the domain has to be one dimensional, right? That's what I mean. So for a curve is, let's come to curve later. Let's have a function which has domain R and domain, which has domain in R, and your range is, let's say, in Rm, where M could be anything. Let's take in particular, let's take R2. For example, let's take fx is equals to x comma sin x, right? I can take this. This is in R2, this is in R. Then the range of this thing, this is a curve in Rm, right? So the range of this curve, range of f is called, or range of curve in Rm. In this particular example, we have f is called a curve. So let's continue with this particular example only. Let's say you have a function f from D contained in R. That means your domain is in real numbers and your codomain is in R2, and the function is defined to be fx is equals to x comma sin x. Then what's the range of this function? We say that the range of such functions, range of these curves, range of range of functions, not a curve, I should write range of function from D contained in R to Rm is called a curve in Rm. So we're taking the example where m is equals to 2, right? This is the example that we're taking. Let's say your domain is fixed. It has to be a part of, it has to be a subset of R. Your codomain can change, and I have taken it to be R2. And the function I've defined to be this. Then what's the range of this function? I say that the range of such functions, the range of functions from R to Rm is called a curve in Rm, right? What's the range of this function? It's the collection of x comma sin x for x belonging to R, right? Is this okay? Is still this part clear to all? Are we going too fast? Is what we've done so far clear to all?
No, ma'am, it's fine. It's clear.
Okay. So in case anyone finds the pace too fast, you can just unmute yourself and let me know. I'll slow down. So this,
Ma'am, what is the function you said? X multiplied by sin x, right?
no, this is x comma, this is from R to R2. So this is a two-dimensional, the range is two-dimensional, right? By two-dimensional, I mean it has to have two tuples here. It's in R2, right? How can I have x sin x? X sin x is
Oh, okay.
not in R2, right?
So, ma'am, that means for x it is r, and sin x it's minus 1 to 1. That should be the range of this tuple.
What's the range of a function? Let's say if you have a multivariable function, let's say you have fx is equals to fx y z is equals to, let's say I have something like this, x comma y plus z comma z square. Then what's the range of this? Range is simply the collection of outputs that you can get, right? That's the range,
Yeah,
right?
ma'am. So for this type of tuples also, like I mean, specifically we see the individual parts and then comment on the range, right? Like for x, we know our range is r, and for sin x it's minus 1 to 1.
Yeah, that's
So,
fine. But we were not actually getting into that part of range and finding the range of multivariable functions or vector valued functions. I just wanted to know what range means. I just wanted to see
oh,
if you
okay,
can figure out the set that represents the range of a function.
okay,
So
I
this
got
is
it.
that, okay? So this is the set that represents the range of f, right? The collection of all the x comma sin x type of tuples where x is coming from real numbers. This is real because the domain of this function is real. Now, if I'll change it to, let's say, 0 comma 1 contained in R, if I'm saying the function is from 0 comma 1 to R2, then the range of f will be this thing, x coming from 0, the collection of all the tuples of the kind x comma sin x, where x is coming from 0 comma 1, right? Because we have the domain this here. So this time, because we simply had R here, that's why your x can come from R. That's the range of your function. So this thing is called a curve. This can represent a curve or is a curve in R2. So if you'll have R2, what's the range of f? Range of f is x comma sin x, right? So the collection of these type of points is this, right? The graph of sin x is the collection of these kinds of points, right? How do you define the graph of a function? Let's say if I have fx is
The
equals to,
x-axis is the
right,
domain and the y-axis is the range.
if I have fx is equals to sin x, then the graph of this function, graph of f, is exactly the same as this thing, right? It's the same x comma sin x type of tuples where x is coming from R. So that means a curve of, let's say if your function is given from R to Rm, then a curve is simply this thing, collection of x comma sin x type of elements here. You'll collect these things and this will, now this is a curve, right? Collection of x comma sin x type of points looks like this only. This is the collection. If I'll collect all of them, then I'll have this curve.
Ma'am,
It's the same.
generally this is the graph of sin x only. So like you were saying that this tuple, I mean this graph is also equal to the graph of sin x, right?
Okay. This, let's say if you have, this is function fx is equals to sin x, right? The graph of this function is x comma sin x. You've studied this, right? Even if you haven't, this is the graph of a function. If you have a single valued function, one variable, single valued function, then that means the graph of that function is x comma fx type of tuples, right? This is how you represent the graph
Okay.
of a function, right? Of a single,
Yeah.
of a function from R to R. I'm only talking about a function from R to R. And
Yeah,
that's how you
yeah, ma'am.
represent the graph, right?
Yeah,
Now, but this is a different function. The f that we've taken here is a two-way, this is a two-tuple function, right? This is a vector valued
yeah,
function.
ma'am.
It's not a single valued function. So in this case, what's the
Yeah,
graph of this function? The graph of this function will be comma, x comma sin x, right?
yeah, ma'am.
But we're not talking about the graph of this function. We are talking about the range of this function. The range of this function is the collection of all these type of pairs, right? X comma sin x type of pairs is the collection, is the range of f. And if you'll plot the range of f, that gives you a curve. This is a curve, right? In R2. So that's what a curve in R2 looks like. A curve in R2 in simple loose terms means that if I, in R2, a curve simply means, that was the proper definition of a curve. That means this is the R2 plane, right? We have chosen the R2 plane, which is a curve in R2. And then you can draw anything loosely here. This is a curve, right?
Yeah, ma'am.
And you can have something like this as well. It doesn't have to be a function. You can take this thing as well. This is also a curve. Not a function, but it's a curve, right?
Yeah.
So that's it. That's a curve for you.
Okay,
So,
I got it.
or in even simple terms, you can just say that it's a trail of points. This is a trail of points, right? You have a lot of points accumulated together, but it's a trail of points only if you see each point individually. And then if you'll collect them together, you'll get the curve, right? That's what a curve is. Now let's say you have, we'll do some more examples. Let's take an easy example. Let's say you have a line in R2. We're only taking curves in R2 for now. A line in, if you look at this thing in R2, a line is this. So it is a trail of some points only. That's why it's a curve, right? If you look at it, if you want to figure it out graphically, that's how you can figure out. By the definition, it should be, if you're talking about a line in R2, let's say if I'm talking about this line, and I want to know whether this line is a curve or not, this line. This is the line y is equals to x, right? Then for this line to be a curve, it should be the range of some function f, where f is a function from this thing to R2, right? If I want a line in R2 to be a curve, then it should be the range of some function of this kind of function, right? What's the range? Can it be the range of something? So if you'll take the function to be, let's take this to be x, and let's take this thing to be x comma x. Now it's a function from R to R2. What's the range of this function?
Ma'am, range is entire R2.
No, it's not entire R2. How is the range of this entire R2? Will you have 1 comma 2 in the range of this function?
No, no. It is like 1 comma 1, 2 comma 2, 3 comma
Right.
3 like that.
So in simple words, you can say it's of the kind x comma x where x is coming from R in simplest terms, right? You don't have to do anything here. Or in other words, you can say because this is the x tuple, this is the y tuple. So you can say that your x should be equal to y, right? This is the x tuple, this is the x coordinate, this is the
Yeah,
y
ma'am.
coordinate, right? So your x coordinate should be equal to the y coordinate. That means all the x y's such that your x is equals to y. This collection should be a range of f, right? And this is a line, right? Isn't it? This is the same line, right?
Yeah,
Y is
ma'am.
equals to x line. So that means it is a curve. Okay, let's do one more thing. Let's say you have x comma y. We are taking xy is equals to 1. So I don't know if you guys know this, but the curve, this thing looks like this. If I have the collection of all the points x, y, such that the product of the two should be equal to 1, then it is, if xy is equals to 1, then x is equals to 1 by y, or I can say y is equals to 1 by x, right? It's the same thing. This means it's the collection of all the x, y's such that, or let me just say, can I write this thing as, I'll keep x as it is. And in place of y, because this is the collection of x, y's, where the product of these two should be equal to 1. So if I'm taking x to be the first one, first tuple, then the second one should be what? It should be 1 by x, right? Does anyone have a doubt in this? No doubt then. Okay. So that means it's the collection of all the points x comma 1 by x, or I can simply take this as, because this is just x, so this is x, and if I'll take x comma, if I consider this to be fx, because it's a function of x indeed, then this is, these points are of this kind, where fx is equals to 1 by x, and this is the graph of fx is equals to 1 by x, right? Graph of f 1 by x looks like this. So this is also a curve. This is a curve because I can write this as, for a curve you need it to be, you can take this to be f from, what's the definition of a curve? It says that it should be from R to Rm, or something, a domain in R to Rm. So I'm choosing Rm equals to 2. This will be 2. And I can take this to be fx is equals to x comma 1 by x. Because this set is the range of this function, this kind of function. That's why this is a curve. Is that okay?
Yes, ma'am.
So that's it. Curve is, please remember, it's the range of these kind of functions. A function whose domain is in R to Rm, these kind of functions range is called the curve. And a curve in R2 could be any trail of points, like this one, like the one we did here, like the sin x one, like this one, like these ones. All of these are curves. Okay.
this applicable only from R to R2?
No, no, it's in the definition I've
R
written
to
Rm, right?
R3. R3,
I've
okay.
written I've in the definition we have written R to Rm. That means, or more particularly, just 1 second. This is not working. Yeah, more particularly, if you have, it's simply the range of a function f. R I'm using to denote range. So your curve is, I'll write this here. Just 1 second. Curve in Rm. We were discussing R2 only, but a curve in general in Rm space is range of a function f. This is range. Range of f where f is a function from R. If I say that it's a curve in Rm, then your function should be, or let's not even take R. It has to be from a subset of R to, it can be from R as well. That's fine. You can take it from R to something or from a domain of R to Rm. So the domain should be a subset of R and the codomain should be Rm, where you say this curve is. If I say this is a curve in Rm, then this should be Rm. Is that okay? We can take an example from R3 as well. Let's say you have, let's say you have a function from R to R3 where we're taking fx is equals to x sin x and cos x, right? So if I'm taking this thing, the first coordinate does not have to be x. You can take it to be something else as well. It could be tan x. That's fine. I'm taking it to be this one. Then range of f is the collection of all these points, right? X comma sin x comma cos x, where x is coming from R. Can I plot these points in R2 plane? I'll obviously have to have R3 plane, right? Because I have three tuples here, so I'll have to have R3 plane. And the range, when I'll plot the range here, that will give me the curve in R3. And this, as far as I remember, is the helix curve. So this gives you the helix one, where I can't draw this, but you can check what helix looks like on internet, and then you will know that it's a curve in R3. Okay, curve in R3 means this. It could be anything in R3, like this. This one does not look like this. This is just a rough example for you to see that in R3 a curve looks like this, where it's varying across x-axis, y-axis, z-axis. It could vary anywhere, right? Is that okay?
Yes, ma'am. Thank you.
Okay.
Yeah, ma'am.
So then we'll move to
Ma'am, can we plot this graph in Desmos?
this one. I don't know. You can
Yeah.
check. This is,
Okay, ma'am.
you can check if it works there.
Yeah, ma'am. I'm
So,
checking right now.
okay. Then we're moving to the topic of limits. So limit is basically, you've done limits in one variable functions, right? Where limit simply means when you have a function. Let's first discuss it for one variable function. When you had a function from R, from a domain in R to R, it used to be like, if I'm saying x tends to A, this means when x keeps coming closer to A, where does our fx go? And if I say that this is equals to L, that means when x keeps coming closer to A, your fx keeps moving closer to L, right? So that was the limit thing for one variable functions. Now let's discuss it for more variables. And before moving to the limit thing, we'll discuss some other terms as well. Let's say when we used to discuss limits in one variables, we used to discuss this concept as well, right? We used to say that if xn is a sequence which tends to A, then f of xn for every sequence that converges to A, fxn should converge to L, right? Remember, this was one of the definitions. Do you guys remember the concept of limits from Maths 1? You guys have done it there, right? Should I discuss that here?
Which one, ma'am?
The limit, the concept of limits in one
Yeah,
variable
ma'am.
functions.
Yes.
Yeah, yeah.
You've
There
done
are
that
some
there, right?
standard formulas also.
Yeah. So if your function, if I say that fx tends to L, then the other way of saying is that whenever I have a sequence that converges to A, then fxn should converge to L, right?
Right.
That was, it's called sequential criteria, but you don't need to know the name. You should know this thing is true, right? So for us to discuss limits, it's very important to see how sequences work as well. We know how sequences look in R. If I have a sequence in R, let's say if I have a sequence, this is how you denote sequences, xn. And if I say that this is a sequence in R, then it looks like this, right? Then your xn could be, you can take 1, 2, 5, or a sequence simply is this thing, right? Where you have collection of scalars. That's it. 1, 2, 5, 7, 3, 26, right? And it keeps going on. This is a sequence, right? So this is what a sequence looks in R. Now, how will a sequence look in R2? If I say xn is in R, or I should say xn tilde, because if I say this is in R, let's say it's in RK. Let's take in R2 only because K becomes confusing. If I have a sequence in R2, then what will be the sequence? What will the sequence look like? It's a sequence is simply endless collection of points coming from here, right? So endless collection of points coming from R2 is a sequence. If I'll take 1 comma 2,
1 comma 2,
2
3
comma
comma 4,
3,
5 comma
yeah,
6.
let's take
Any
this one,
point in R2 plane.
3 comma 4, 4 comma 5, and so on, so on. This is a sequence, right? It's it's an endless collection of endless, and you can number them 1, 2, 3, 4. So it's an endless collection of elements coming from R2. So a sequence in R2 is endless collection of elements coming from R2, right? So what should a sequence look like in, let's say if I want to take a sequence in Rm or Rk, let's say, then what will the sequence look like? It will be, I can take x1, x2. I'm taking these things here, x2, x3, so on till xk. And I'm taking one here. So one, I should call this x1 tilde, right? So the point x1 tilde is x11. This is the first point in your sequence. Then the second point in your sequence you can take as x21, x22, x23, and so on till x2k. Then the third point in your sequence will be, similarly, you can do a third point here. And similarly, you can do the nth point here. This will be n1, xn2, and xnk, right? And because this is a sequence, so it is supposed to never end, right? Sequences never end. So this is never going to end. It will keep going on like this. So this is how a sequence looks like in RK. A sequence in RK is an infinite collection of k tupled elements. This is a k tupled element. This is a k tupled element. This is also a k tupled element. There are k tuples here, k tuple here, And this is an infinite collection, right? It keeps going on. X1, X2, X3, Xn, then so on, so on. So this is what a sequence looks like in Rk. Like let's say, example you can take. Let's take a sequence in R4. So a sequence in R4 can look like 1 by n, 1 by n square, 1 by sin n, and 1 by cos n. This is a sequence in Rn, R4, right? You have four tuples here. If I'll take what is x1 tilde here, the first element of your sequence is 1,
1, 1 by 2, 1 by 3, 1 by 4.
1, and 1 by, it should be sine 1, right?
Yeah, ma'am. Yeah.
Then you will have cos 1. So this is the first element of your sequence. Then the second will be this thing.
2, 1 by
1
4,
by
1
2,
by sine 2.
1 by 4. And then you will have 1 by sine 2, 1 by cos 2. And then so on, so on. Then you will have xn. So nth element will be this thing, 1 by n, 1 by n square, 1 by cos n, and 1 by, sorry, 1 by sin n, and then 1 by cos n. Then 1 by cos n, right? And it, because it never stops, so it will keep going on. Then you will have xn plus 1, xn plus 2, xn plus 3, and so on, so on. So that means, so this that means the sequence in Rn or R4, sequence in R4 is basically collection of sequences only, right? That means it's a collect. This is one sequence, second sequence, third sequence, and fourth sequence. You just need to have, if it's k tuple, first tuple, second tuple, this is third, this is fourth, let's say this is fifth. If it is five tuples, then you should have a sequence here, a sequence here, a sequence here, a sequence here, and a sequence here. So that will give you a sequence in R5, right? So a sequence in Rn simply looks like collection of sequences. One sequence here, sequence 1, sequence 2, sequence 3, and these sequences are from R to R, right? Sorry, N to R. So, or let me just write it clearly. If I want to take a sequence in
Ma'am,
Rn, yes, just 1 second.
for this, yeah, yeah.
A sequence in Rn is, if you want a formal definition, it will be a sequence in Rn is a function from N to Rn, right? That's how we used to define sequences there as well. That means you will have f1 here, some value from Rn, then f2 here, some value from Rn. So that is how you define. That's a formal definition of a sequence in Rn. It's a function from N to Rn, or you can, in other words, what can I say? A sequence in Rn is, in simple words, it will be n tuples here. So it will be sequence 1, sequence 2, so on till sequence n. And where are these sequences from? If this entire thing is a sequence in R4, then individual ones are sequences in R1, right? These ones, if you look at them individually, there are sequences in R1. But this entire thing is a sequence in R4. That means whenever you have a sequence in Rn, it's the collection of sequences in R only. This is from all of these. This one, all of these are sequences in R, right? Is that okay? So if I have to find the limit of a sequence in R4, let's say, if I have to find the limit of this sequence, then how should I find it? I need to find the limit of individual sequences involved, right?
Ma'am, here, like you were saying that you have to like find the limit of individual R1. So, ma'am, like previously you said that we are defining a domain for each of the sequence individually, but aren't we supposed to define a common domain for the entire Rn?
For which domain a sequence is, this is a sequence. A sequence in Rn is, your domain is same only, right? It's natural numbers here. And what's the domain here? What's the domain of a sequence in R? A domain of sequence is always R, is always natural numbers. This matters. When I say a sequence in R, I mean the codomain is R. Domain is always natural numbers. For a sequence, the domain of sequences is always natural numbers, right?
Okay, okay. I
So
got
your domain for this entire thing, for these individual ones, is also natural number, and the domain for this entire tuple is also natural numbers. These individual ones are sequences in R, and by that I mean that they take, if I have 1 by n, then the value of 1 by n is going to be in R, right? N doesn't need to be from R. It is a natural number. N cannot be from R. I can't take 2 by 3 here because 2 by 3 is, n equals to 2 by 3 is not valid because that's not a natural number. But my 1 by n can be in real numbers, right? That's what I mean when I say a sequence in R. That means it takes value from R. Is that okay?
got it, man. Yeah.
Okay. So we were discussing this thing. So if I want to find the limit of this thing, let's say, let's come to this. Where is it? This one. Let me just write this thing again. If my sequence is xn tilde and my sequence is this 1 by n, 1 by n square, 1 by sin n and 1 by cos n, then how do I find the limit of this sequence? This should be simply find the limit of this, find the limit of this, find the limit of this one, and then write it. So what's the limit of 1 by n? 0, right? So this will converge to, let's see where it goes. 1 by n, the first tuple goes to 0. Second one also goes to 0. And let's come to this one. When n tends to infinity, where does this go?
Not
Yeah, so it's not defined. This one is not defined. Does not exist, does not exist. So if the limit of any of these does not exist, let's say if I have involved sequence 1, sequence 2, sequence 3, sequence 4, 5, 6, 7, 8. This is in R8 and I've involved 8 sequences. Then the limit of all of these should exist. Then is when I say that the limit of this entire sequence. This is also a sequence, and individually these are also sequences, right? So if I say that the limit of this sequence, this entire sequence, tuple sequence, a sequence in R4. This exists if the limit of these individual ones exists. And if any one of these, if the limit of any one of these does not exist, let's say here the limit of the two does not exist, right? Let's say if I'll take 1 by sine 1 by n, right? So if n tends to infinity, 1 by n tends to 0. So sine n also tends, this sine thing also tends to 0. And this, we know this tends to infinity. We can't say that it does not exist, right? Or let me just simply take, what's better is let's take sine 1 by n. That's better. Now, if I'll take sine 1 by n, then the limit of sine 1 by n is 0 again, right?
0.
0. So the limit of this exists, this exists, this exists. Only the limit of this does not exist. This is a problem. But even if one of the limits does not exist here, that means the limit of this entire sequence, this tuple sequence, this thing does not exist. Is that okay?
Got
Okay. So we'll see one more thing here. Let's take one more example for clarity. Let's say you have 1 by n square sine n by n, then 1 minus cos n by n, and summation 3 to the power k factorial, k varying from 0 to n. This is a sequence, right? Where is this a sequence? Is this a sequence? It's a sequence in 1, 2, 3, 4. So it's a sequence in R4 again, right? And for me to be able to find the limit of this sequence, which is in Rn, R4, I should be able to find the individual limits, right? What's the limit of this thing? This goes to 0. This one goes to, when n tends to infinity, sine n by n tends to 0, right? This sine n is between. Okay, when you guys don't say anything, I assume that you've understood this thing. So if anyone has any, or else I over explain things. So that's why I want you guys to respond. The limits, you can tell me the limit of these things. So the limit of this one is 0. What's the limit of this one? Your
0.
sine n, right? This is also 0. And what's the limit of this one?
Ma'am, it is 0 by 0 form.
It's 0 by 0 form, but the limit can be found, right? Your
Yeah, yeah,
actually your
definitely.
sine n, and this one is not even 0. How is this 0 by 0 form? When n tends to infinity, sine n is, it is between -1 and 1, right?
Oh, I was not
Sine n
talking
is,
about the.
yeah.
I thought limit n was approaching to 0.
No, this, when you take sequences, n always approach to infinity. Limit of a sequence means, when I say limit of an, it automatically means an when n tends to infinity, right? That's the meaning of limit of a sequence when n tends to infinity. Okay. So if I have sin n between -1 and 1, that means this numerator is finite and your n can tend to infinity. That means this thing will go to 0, right? And same goes for this one. 1 minus cos n is always a finite number, but your n can go to infinity. That means this entire thing will go to 0. And what about this one? The limit of these x to the power k factorial, this is factorial. Summation k varying from 0 to n. This is a sequence, and the limit of such sequences, these type of sequences, is e to the power x, right? So that means the limit of this thing should be equal to e to the power 3. So the limit of this entire four tuple sequence will be 0, 0, 0, e to the power 3. Okay, then we'll do, if you have a, if you have the limit of a scalar valued function, let's say, or if, let's say, if you have a function from Rn to R, then how do you find the limit of this one? It will be fx tilde, or we'll come to this one later. This simply means, what this means is, if I say a function from Rn to Rm, that means it's this kind of function, x1, xn, and some value of this kind of function is there. And the value is, this belongs to R, this kind of function. Then the limit of fx, I'm denoting this entire thing by x tilde. As x tilde comes closer to a tilde, this will be a number, right, in L, in R. So this means when x tilde comes closer to a tilde, that means if you have x1, xn, and you're trying to find the limit at 0, 0, that means when each of these individually approach to 0, that means if This means if this point keeps coming closer to 0, the other one also keeps coming closer to 0, all of these keep coming closer to 0, then where does our function go? Or in this particular case, it will be a tilde here, right? So if it's a tilde, it will be when x1, this variable comes close to a1, second variable comes close to a2, and the nth variable comes close to an. Then where does our function go? Where does this thing go, right? Let's say you have, so we'll do some basic limits first. These are not examples, these are basic limits that you should know. So your basic limits are xi to the power k. Let's do the limit of this. When, let's say, x1 to xn, this is a variable, approaches to a1 to an. Then what will be this limit then is ai to the power k. That means if I'll take, or in particular, if I'll take x10 to the power k should be equal to a10 to the power k. First, and second, we have, if you have e to the power xi, when x tilde moves to a tilde, moves close to a tilde, this should be equal to e to the power ai. The third one is for log, where log xi, when x tilde keeps coming close to a tilde, that means x1 comes close to a1, x2 comes close to a2, and so on, so on. So log xi will come close to log ai.
AI.
So these are the basic functions where you can just replace xi with an ai, that's it, and no problem will happen. And then we have
And
limit.
this is for these multivariate functions, right?
If you look at this function, actually, e to the power xi, then it's a single variable function only, right? Because you just have xi here. But if I'm saying,
No, ma'am.
yeah,
I was seeing that you have written na previous one x1 up to xn approaching to a1
yeah,
a2 up
this is
to
for
an.
multivariable functions, right? This one is for
Achha.
multivariables.
Okay.
Then the basic ones where you have limit of f plus g is the same as limit of f plus limit of g. Limit of f minus g is the same as limit of this, limit f minus limit g plus minus. Similarly, you have other things too, where you have the multiplication rule, which says limit of fg is the same as limit of f limit of g.
And this thing I been
What? Do we have any doubt? Limit of g, provided g x is not equals to 0, right? I should say gx is never 0. We should have to, we need to make sure that gx should not be 0, right? For any x. That means 0 value should not be here. When x tends to a, this will be x tends to a, x tends to a, x tends to a. All of these are these limits, right? Same thing, same thing. Okay. Does anyone have a doubt so far? We haven't really discussed anything which is very complicated. But does anyone have a doubt in anything that we've discussed so far? Okay. So, and then next up we have our sandwich principle, which says we don't have a T here, right? So our sandwich principle is simply it's the same. You've done this thing too in Maths 1, but this is just generalized to Rn. Earlier, you used to do this for R, the functions, the single valued functions, one variable functions. Now it's for more than one variable functions, right?
Then we used to do a
Multivariable
sandwich
functions.
theorem.
Yeah. which was if hx is a function which always takes values between the function f and gx tilde. And if I say that limit of fx tilde is the same as tilde I'm using for x1 to xn, these kind of tuple things. If you have this thing, and if I say limit of fx for all x tilde belonging to the domain, right? So that means if I'll take f1, then f1 is less than h1, although 1 is not this kind of number, but still. I just want you to know what this means, that f1 should be less than equals to h1 should be less than equals to g1. This is what it means. Similarly, f2 should be less than equals to h2 should be less than equals to g2, right? So when we say that this is happening, it means that for a particular x tilde, the function's f's value at x tilde at a particular number, at a particular element, is less than h's value, is less than g's value. So, and if I say that, and if limit x tilde as it moves closer to a tilde is the same as limit g x tilde as x tilde moves to a tilde. That means at a particular point, a tilde, if I say the limit of this one and this one is same, let's say this is also going to L, this is also going to L. Let's say that means H will also come, it will also move to L. So this implies Hx tilde, limit of Hx tilde as x tilde moves to a tilde is also L. That means Hx tilde in simple words, it's this thing. If this goes to L, this goes to L as x tilde tends to a tilde, then hx also moves to L as x tilde moves to a tilde. Is that okay? The same thing that you used to do in one variables. It's the same thing.
Yeah, ma'am.
Then we have, just 1 second. So next up we have limit of scalar valued kind of functions. See, if we're discussing scalar valued functions in particular, why? Because even if it's a vector valued function, we've just seen if it's a function where it looks like this. Let's say if I say if it's fx equals to x square, x to the x plus 1 and sine x and so on, then for me to be able to find the limit of this function, I'll need to find the limit, these limits individually, right? That's what we did there. When we said 1 by n square, we'll need to find the limits individually. First, we'll find the limit of each tuple, and then we'll take them collectively, right? So similarly, if I want to find the limit of this as x moves close to a, if I want to find the limit of this function, what should I do? I should first find the limit of first tuple, which is x. So this limit will be a. This will be a square. This will be a plus 1. This will be sine a, right? And then I'll just collect them together. That's how you find the limit of a vector valued function. That means if you know how to find the limit of a scalar valued function, scalar valued will be this. Fx is equals to sin x. If you know how to find the limit of this one, then you can deal with a vector valued one, right? This one. It's just collection of scalar valued functions only, right? So we'll only deal with scalar valued functions here. So we'll discuss limit of a function of f, which is a scalar valued function, because once we know the limits of scalar valued functions, we can find the limit of vector valued functions, right? Vector valued functions are collection of scalar valued functions only in tuples. That's why. So limit of f will be, let's say, I say that limit of f, it's the same thing. If I have fx tilde and I'm taking it to be a multivariable function, because you already know how to deal with a one variable function. So we're not going to talk about those ones. I'm talking about a multivariable function where this is of the form fx1, and so on till xn. These kind of functions. If you have to find the limit of this thing, limit x tilde tending to a tilde, then what's the limit? And this is a scalar valued function. That means fx tilde, this is a vector, but the value that you will get will be a scalar, right? This will be, let's say, something here.
Yes.
Let's call it y. So that means if you have to find this thing, then it should be when x tilde comes close to a tilde. That should mean that when a n tilde, when you have a sequence, if you have to find this limit, what should I do? Let's say this limit is L. Then we've discussed this thing when we had fx here, we discussed this, right? That there, if xn tends to a as x tends to a, I say that this is true if and only if xn tending to a means fxn for every sequence tending to a, fxn sequence should tend to L, right? So similar thing will happen here, and we'll do if x tilde n, because you're taking sequences in n tuples, right? So if xn tilde tends to a tilde for all xn tilde, that means if there is any sequence that converges to a tilde, for that sequence, fxn tilde should tend to L, right? So this is what we have to do. Now let's take one example. Let's do this one. Let's say you have fxy. I'm only taking x1, x2. That means I'm only taking two things here. I'm not moving into more than two. This will be x square minus, let's take this to be x square minus y square by x square plus y square. And I want to find the limit of this function. Let's say I want to find the limit fxy when xy tend to 0, 0. That means when x comma y, this is in R2, your 0, 0 is here, right? This is your 0, 0. And what are we trying to do? We're trying to figure out when x comma y, that means when your pair x comma y keep coming close to 0, 0, and it can come close to 0, 0 from this direction, come close to 0, 0 from this direction, from this direction, from this direction, right? From any direction, if I'll approach 0, 0, where will my fx comma y go? Where will this thing go? Right? That's what we have to find. So if x moves to 0, if I'll just substitute the values, I'll get 0 minus 0 by 0 plus 0, which is 0 by 0 form. That means we can't directly find the limit by substituting the value here. X equals to 0, y equals to 0. But let's do one thing. If I have, what does the definition say? Can you compare this function to this thing? Firstly, x tilde is x comma y, because we have n tuples here, but we've only chosen the case of two tuples. This is a scalar valued multivariable function, right? Multivariable function. So if I have to find the limit of this thing, and if the limit exists, let's say this limit is equals to L. If I say the limit exists and the limit is equals to L, what does it mean? It means that whenever I have a sequence xn comma yn, if I have a sequence xn comma yn going to 0, 0, then my fxy, this should imply that my fxy should go to L, right? If whenever I have a sequence xn comma yn and it goes to the point, this point 0, 0, then my fxn comma yn should go to L. That's what this limit means, right? That's what the definition says here. So if I'm able to find, let's say if I have xn comma yn going to 0, 0, and then my fxn comma yn goes to L, and if I have another sequence xn dash and yn dash, and this is also going to, this is another sequence, right? This is a sequence in R2. This is another sequence in R2. This is also going to 0, 0. And then if I see that fxn dash, yn dash, this is going to, let's say, L dash, which is not equals to L. What does this mean? This means if I am approaching this path, that means from one path, the limit is something else. But if I'll approach this point from some other direction, my limit is coming out to be something totally different. That means the limit does not exist, right? The same way we used to do in two variables when we used to say this is a two variable function, right? In one variable, what we used to do, if this is a point, we used to say if I'll approach this point from this side, because there were only two directions of approaching this point, this side or this side. We used to say if our left hand limit is the same as right hand limit, then the limit exists, right? And if both of these limits are different, that means a limit does not exist. So the same concept we're using here. In R, when you have a function from in one variable functions, you only have one direction to approach a point. That means the domain is R. That means it's just a straight line. It's the line, right? The real axis. So if this is your point X, there are only two directions to approach your point. The left one, this direction, this path, and this path. There is no other path, right? Can you find any other path on this line to approach this point X?
No.
And it should lie on the line only. You can't take the path from here. You can't do this because this path is not on this line. That's why. So for that, and we used to say that if left hand limit does not exist, then the limit does not. If one of these limit, left hand one or right hand one, if it doesn't exist, that means limit does not exist, right? If they're not equal, then also limit does not exist. So same happens here. When you have a function from Rn to R, and let's say you are saying that my point, this time my point will be x1, so on till xn, converging to a1, so on till an. Now if this is my point, a1, a2, so on till an, then this point is in n-dimensional space, right? In particular, if I'll take we can't visualize n-dimensional space. So let's just take two-dimensional space. If I have a1, a2, then the directions to approach, and this is in R2, right? A1, a2, that means we are in R2. So how many directions do I have to approach this point? In R2.
Directions.
Two directions.
Four directions.
How is it 4? Okay. If this is my point A1, A2, I need to find directions to approach this point such that all the directions are in my R2 space. I want an R2 spaces is it's not just these axes, it's the entire space, right? R2 space is like a paper. If you have a paper, that's an R2 space, right?
Yes, ma'am. A plane.
Right. So it's a plane. Now, if I have to approach this point on a plane, if you have a paper and you have a point, this is a paper, this is a point, and I want to approach this point such that the direction of approaching this point should lie in this plane. How many directions would I have?
Two.
You'll have infinitely many directions, right? You'll have this direction, then you'll have this direction.
Oh,
Choose
yeah,
whatever
yeah.
direction you want. There is no restriction. I just want the only restriction is that the direction, the entire, if you're approaching this point, and if this is the path I'm choosing, then this path should be in the plane. That's it. That's the only condition. I can't move out of this plane. That's it. So that means if I have XY plane, then I can choose. My only problem will be I can't take something like this, X, Y, and then Z is equals to 1. I can't take this thing, right? I can't move out of this plane to approach this point. So to approach this point, I have this direction, this direction, this direction, this direction. Now I have so many directions to approach this point. That means from every direction, like we used to do in R here, if you have a straight line and you have a point here, you only have two directions to approach this point such that your direction of approaching your path should remain in this line. I want that path to remain on the line. So there are only two ways, either this one or this one. There is no other way, right? That's why we have the concept of left hand limit and right hand limit there. But here you have so many directions to approach the point itself, right? So that means each direction matters here. That means if from this, let's say from this direction I'm getting L1 limit, from this direction I'm getting L2 limit. From this direction, let's say I'm getting L1 limit again, and from this one, I'm getting L1 again. That means that my limits are not matching, right? If from every direction I get L1, that's fine. That means, and by every direction, I mean whatever direction is possible. From this direction, there are infinitely many
Ma'am,
directions to approach this point. Yes.
ma'am, even if in one direction the limit is coming something else from the other, we say limit does not exist, right?
Yeah. If any two directions limit does not match, that means the limit does not exist. You don't need to find others. But if two
Okay,
directions,
ma'am.
let's say from if this direction it's L1, from this one also it's L1, from this one, and you've checked, let's say 10,000 cases where from all directions, 10,000 directions, and fx, the limit of fx always comes out to be L, let's say. That does not mean that the limit is L. You can still find, because there are infinitely many directions and you can never check infinitely many directions, right? So what does this leave us with? This
Yeah,
tells
ma'am.
us that it's easier to disprove that the limit is not. You can easily disprove things, right? If a function's limit does not exist, you can find two directions and say that the limit from this one is different from the limit from this one. That's why the limit does not exist, right? That's easy. But if you have to prove that the limit is equal to this thing, let's say if I have to prove that the limit of this function fx is L, then I'll have to check for infinitely many directions, which is actually never possible unless you have some other rigid way to prove this, right? So this thing, similarly in this case, when you have this thing, when we say that if I say that the limit is equals to L, then I say for all sequences converging to A, this is the same thing, right? There we were discussing about directions, it's the same thing here. For every sequence converging to A, my limit should be same. It should be same L. It should not vary, right? But if I am able to find two sequences such that this is what's happening here. Let's say if I have one sequence this x and y and another sequence x and dash y and dash, and my limit is coming out to be different. That means limit does not exist, right? Limit of fxy as xy tends to 0, 0 does not exist. This does not exist because two directions are giving two different limits. Okay, then coming, that means if you want to show that the limit of this does not exist, then it's enough for you to find two sequences such that they both converge to 0, 0, but fx and yn does not go to L, or it goes to two different limits using these two. So let's do this one here, right? Let's do this example. You have x square minus y square by x square plus y square. When you have this function, I just need to have two sequences. So I can take, if I'll take this to be 1 by, if I take x coordinate to be 1 by n and y coordinate to be, let's say, 0. If I'll take this, then what will happen? Then fxy, that means I have a sequence, one sequence, this sequence converges to, I have to find the limit of this when xy tends to 0, 0. So let's take this sequence, this converges to 0, 0, right? And what will be the limit of this function then? F of 1 by n comma 0 when 1 by n comma 0 tends to 0, 0. So this is just the 0 sequence. You can eliminate this one. What's f of 1 by n comma 0? Put x equals to 1 by n here. You will get 1 by n square minus 0 by 1 by n square plus 0. So this is just 1, right?
Yes, ma'am.
That means the limit, that means your function at 1 by n comma 0, all these type of numbers is always 1. That means the limit is also 1. It's a constant function. That means limit of f1 by n comma 0 as 1 by n comma 0 moves to 0, 0. Or instead of writing this thing, I can simply write, because I already know that 1 by n comma, when n tends to infinity, 1 by n comma 0, we've chosen those kind of sequences which go to 0, 0 when n tends to infinity, right? So I can simply write n tends to infinity here. Is that okay?
Yes, ma'am.
So that means this will be, I can simply take n tending to infinity here. So this will give me 1 because it's a constant function on these kind of tuples 1 by n comma 0, my function becomes constant. So the limit will be 1, right? Now let's take another sequence. Let's call this sequence 1 via sequence 1. So this is limit of the function via this sequence, right? This is a sequence that goes to 0, 0. Via this sequence, your function's limit is 1. Then via some other sequence, let's take 0, comma 1 by n. This is also a sequence that goes to 0, 0. So
Yeah.
my f of x comma y, or you can just say, if I'll put 0 comma 1 by n here, I'll have x square minus y square. So 0 square minus
-1.
1 by n square by 0 plus 1 by n square, right? So this will be minus 1
Yes, ma'am.
as n tends to infinity. So that means the limit
Path
of
independent.
f
Does not exist.
via, yeah, it does, 1 second, limit of f via the sequence 1 by n comma 0 does not, this is 1 minus 1, and limit via the other sequence was 1. And because you found two sequences, that means you have two ways that lead you to 0, 0. Both of them are going to 0, 0. This path is also leading you to 0, 0, 1 by n comma 0, and 0 comma 1 by n is also leading you to 0, 0. But the function is giving you different limits when this tends to 0, 0 and when the other tends to 0, 0. That means because limit via 1 by n comma 0 is not equals to limit via 0 comma 1 by n. This means limit does not exist. Let's do one more example. Let's do this one. Let's say you have xy, x square plus y square when xy tends to 0, 0. So if you have to find this limit, this is again multivariable scalar valued function. So this will be, if I'll put x equals to 0, y equals to 0, I'll get 0 by 0 form. So I can't take that. Let's see if I can find two different sequences, xn yn and xn dash yn dash, such that the function's limit when these two tend to 0, 0, both of them will tend to 0, 0, and the function will tend to something else at both of these. Let's see if that can happen. But fxn yn and fxn dash, and this is dash. Two different sequences converging to 0, 0, but the function's value at these sequences, this is also a sequence, right? They converge to different points, L and L dash. Let's see if this can happen. So if I'll take x equals to, if I'll do the same thing here, if I'll take 1 by n comma 0 and 0 comma 1 by n, it's not going to work this time. Because if I'll have 1 by n comma 0, this thing will give me 0, right? If I'll put x equals to 1 by n, y equals to 0, what will be the limit of this function then? Limit of 1 by n, 0, and then whatever you have in the denominator, it's x square plus y square, 1 by n square plus 0 square. This will just be 0. Similarly, if I'll do it using this one, it will be limit 0 into 1 by n by 0 plus 1 by n square. So this will again be 0, and both of these limits are 0. But this doesn't mean that the limit of this is 0. Because as we have said, you can only disprove using this approach. When you use this approach of sequences, that this sequence is going to 0, this sequence is also going to 0, then where is your function going on this sequence? That only helps you to disprove. You cannot use that criteria to prove things. This proves nothing. If you're getting 0, 0, and then if you'll test 10 more sequences and that will also give you 0, 0, that doesn't mean the sequence limit, the function's limit is 0 at that point. You will still need a valid proof for it. You will have to prove it. So this is, let's try something else. Let's try 1 by n. Taking any one of them 0 is not helping. So let's take 1 by n, comma 1 by n. What will we get then? We have xy by x square plus y square, right? So this will be f of 1 by n comma 1 by n will give me 1 by n comma 1 by n as n tends to infinity is 1 by n. This is x, this is y. Xy divided by x square plus y square. So 1 by n square plus 1 by n square. And this is half,
1/2.
right?
Yeah. Yeah.
So this limit is half. Now if I'll test it via, and the other one was 0, right? We've already found one sequence. From these two sequences, you're getting 0, 0. From this sequence, you're getting half. That means the limit does not exist. Via different sequences, different directions, different sequences mean via different directions, you're getting different limits. That means the limit does not exist. Okay. Then we can use the curve approach too. Now we've used, this time we've used the sequential approach, right? We're using sequences here. When this sequence tends to 0, 0 or the point given to you, we want the function to tend to a particular limit, no matter what the sequence is. Now let's come to the curve approach. So limits using curve is, it's the same approach that we used there using curves. So it's, let's say if this is your point a comma b, and I want to find the limit of function fx comma y when my function converges to, when xy, that means I want to find the limit of fxy when xy tends to a comma a. If a comma b, let's say, if that's what I want to find, then that means when if via this path, if a comma b lies on some curve, let's say this is y is equals to fx curve, and a comma b lie on this curve, that means this curve, if I'll take, okay, let's not get to how we get this thing. Let's just directly come to the questions, because there's not much time left to discuss how we come to this, how we came to this formula. We'll just discuss how is the question supposed to be done using this approach. So let's say we'll use the same thing, right? So first example that we did was x square minus y square by x square plus y square when x comma y tends to 0, 0. Earlier we did it using sequential approach. Now we'll use the curve approach. So that means you just have to find the curve. The first step is find the curve that passes through 0, 0. Curve in R2 obviously, because this is two variable. So curve in R2 passing through 0, 0. Can someone give me a curve that passes through 0, 0?
Ma'am, y equal to x
Curve
square.
or a function. Let's not even take curve. Let's just take a function. Find a function in R2. By function in, let's take curve only.
Ma'am, you can take x square, the parabola.
So that will be, yeah, we can take y is equals to x square, or instead of complicating this, I'll just write find the function
Yeah, ma'am, function automatically
passing
covers
through
all
0,
the
0. Yeah,
graphs. I
yeah.
mean,
So we'll take a function that passes through 0, 0. So you'll have y is equals to x square, right? Or you can take y is equals to x as well. You can take y is equals to 2x. All of these functions pass through 0, 0, right? Y is equals to sine x also passes through 0, 0. You can take any one of these. So the most general will be these things. If you have to generalize, y is equals to x to the power k when k is not equals to minus 1, right? Or not this one, when k is positive, strictly greater than 0. When k is strictly greater than 0, this curve passes through 0, 0. And y is equals to mx. This is the equation of a line. This also passes through 0, 0, right? For all m. So both of these curves pass through 0, 0. Pass through 0, 0 for k greater than 0, and m you can take to be anything. That's fine. So these all curves pass through 0, 0. What you have to do now is you have to put y is equals to, your y is equals to fx, right? So you just have to put y is equals to these things, x square. So let's put y is equals to x square here. So my function is x square minus y square and x square plus y square. That means if you have a function y is equals to fx that passes through this point 0, 0, because you have to approach to 0, 0, xy tending to 0, 0, and y is equals to fx passes, if this passes through 0, 0, then the limit of this will be, then limit of f, let's say this is f, or I should write this thing only, x square minus y square by x square plus y square, limit of this at 0, 0 via y is equals to fx via this curve. That means you have a lot of curves that pass through 0, 0, right? This curve, this curve, this curve. I am taking the y is equals to fx curve in particular. If you have 0, 0 here, then this line y is equals to x. This also passes through 0, 0. Y is equals to, if you will have y is equals to half x, that also passes through 0, 0, right? If you will have y is equals to sine x, that also passes through 0, 0. So these all of these curves pass through 0, 0. Those are the kind of curves that you have to consider and put here. So the limit of this function at point 0, 0 via y is equals to fx will be limit x tending to 0, x square minus f of x squared by x square plus f of x squared. So I've replaced y with fx. Just give me a minute. So we were doing this thing. What you have to do is you have to replace y with this fx, because you're calculating the limit of this function via y is equals to fx, a curve. That's why I'm replacing y with fx. So we'll have this thing, and then because your entire function, which was in terms of x and y both, is now just in terms of x, so you can find the limit of this, right? This is a one variable function. You know how to find the limit of one variable functions. Let's do one example. We were doing this example, x square minus y square by x square plus y square. So limit of this function at 0, 0. Let's take it via, x is equals to y. So via, or y is equals to x, same thing. Via y is equals to x curve will be x square minus, in place of y, I'll put x, this y is equals to x. So you will have x square minus x square by x square plus x square, limit x tending to 0, right? So that's what I was saying, that when you have y replaced and when you have y in terms of x in this expression, everything then will be in terms of x. So this becomes the limit of one variable function then, right? And this is, by the way, just 0. So the limit is 0, right? This limit will be 0. So via this curve, y is equals to x, your limit is 0, right? Now let's test it via y is equals to 2x. Let's do this. You will have x square minus 2x square. So that will be 4x square divided by x square plus 4x square. Limit x tends to 0. Now if I'll take this thing, I'll have minus 3x square by 5x square. So this will be minus 3 by 5, right? So that means via this curve, That means, in simple words, if I approach, I have to find the limit of function at 0, 0. So if I'll approach using this curve, y is equals to x. If I'll approach this point from here, from y is equals to x direction, my limit will be 0. But if I'll approach it from here, y is equals to 2x, my limit will be minus 3 by 5. And those two are different, right? That means limit does not exist. Okay, let's do one more example. Let's say I have sine xy by xy and xy tends to 0, 0. What's the limit of this one? Does the limit exist? Can you find two sequences or curves? Via two curves, the limit is different, or via two different sequences, it's different. So for such functions, if I have xy and I'll replace xy with, let's say, capital T, where my capital T is also xy are variables. So capital T is also a variable, right? So if x comma y is going to 0 comma 0, then where does my xy go? If x comma y
0.
converges to 0, 0, then product of these two also converges to 0, right? That means my t converges to 0. So when my xy converges to 0 comma 0, my t converges to 0, this capital T. So if I replace this xy with the t, I'll get sine t by t, t tending to 0, right? Can I do this? My t tends to 0 only
Yes.
when xy tends to 0. So I can replace these things, right? Now this is a one variable function and the limit of this is
One.
1, right? That means the limit of this does exist. So for you to be able to prove that the limit exists, you need a rigid thing, right? Like this one. You can't just prove it using sequences, that via this sequence, I'm getting 1, via some other sequence, I'm also getting 1, and via every sequence I try, I get 1. That's not the right, then you cannot actually predict whether the limit is 1 or it does not exist, right? So this is the right way to actually find the limit of a function. Okay, let's do one more thing. Let's do this one, where you have x square plus y cube, and here you have x to the power 4 plus y square. And again, obviously, we're taking the limit at 0, 0. And what's the limit of this one? So this one will be, let's try to find, because we don't have any, this one we could directly observe that this is xy and this can be replaced because everything is in xy. Now, if you have something like this, let's say you have 1 minus cos of xy by xy. Now, if you have something like this, then I know that this entire thing can be replaced with a t, right? That's no issue. Or even if I have something like this, or if I have e to the power, let's say if I have e to the power xi minus, or instead of this, if I have e to the power xy minus 1. What about this one? If my xy is moving close to 0, 0, then this is e to the power 0. So 1 minus 1, this is 0. This is also 0. That means I get 0 by 0 form. But I can still use the same approach. I can substitute this equals to t, this equals to t, and then I'll get 1 minus cos t divided by e to the power t minus 1 when t converges to 0. And now the limit is still 0, 0 by 0. Nothing changes. But because we have one variable now, we can use L'Hopital's rule, right? Which says you can take if you're getting 0 by 0 form, you can take the derivative of both of them both of the denominator and numerator. So this will give you sine t, and the other one will give you e to the power t as t tends to 0. So what will you get here? You'll get 0, right? That means the limit of this entire thing is just 0. But for such things, you can't get. Let's first try to find, this is the right way to do things. When you don't see an actual pattern, first you try to find the curve where find two curves such that limit does not match, or find two sequences where limit does not match. So we'll go with the curve thing. So for the curve approach, can you think of two curves here? If I'll take y to the power, let's say, if I'll take
Y is equal to 0 and x is equal to 0.
y is equals to 0 and what?
X is equal to 0. The y-axis and the x-axis itself.
Okay, so you're saying x comma 0 and 0 comma y, is it?
Yeah, ma'am.
Okay. So if you will approach, okay, if you have 0 comma 0 point here, and if you want to approach it, if this is 0 comma 0, and if you want to approach it from here, that means you're taking x comma 0 kind of points, right? X comma 0 kind of points going to 0 comma 0. And if you're going to approach it via y axis, it's 0 comma y kind of points. Okay. So let's take it via x comma 0, or you can say y is equals to 0, right? Let's take it via y is equals to 0. I'll get x square by x to the power 4. Limit x tends to 0. This is 1 by x square. And this will give us infinity, right? This limit is infinity. And if I'll take via x equals to 0, I'll have limit y tending to 0 and everything left in terms of y. So it's y cube and y square, right? So this will give you 0. This limit will give you 0. This is 0. And both of these limits are different. That means the limit of this function does not exist. So one quick way, one tip would be, you can test for general y is equals to mx. If you see something like this, let's say you have x minus y and x plus y. If you have something like this, then if I'll put y is equals to mx, I'll have x minus mx by x plus mx, right? And if I'll take x common from here, I'll get x 1 minus m and x 1 plus m. Now x gets cancelled. And if I'll take the limit as x by 10 to 0, 0, or x tends to 0, what will I get? I'll get 1 minus m by 1 plus m. And it will change when I'll change the m, right? So that means via this, your limit will be limit is equals to 1 minus m by 1 plus m. And it will keep changing if I'll change m, right? That means not a single value, depends on m, and can change. This implies limit does not exist, because for different values of m, that means for y is equals to x, m is equals to 1, you will have something else. For y is equals to 2x, m is equals to 2, you will have some other limit. That means limit does not exist. And the other way is check for y is equals to x to the power k, right? So you can do the same for, like we did here for m, you can do the same for k, like in the example that we took. This one, x square plus y cube and x square plus y cube, and the other part was x to the power 4 plus y square. Now for x, if I'll take y is equals to x cube, what will I get? I'll get x cube plus x to the power 3 x square, right? So I'll have x square here, x to the power 3 k. Then I'll have x to the power 4 plus x to the power 2k, right? So if I'll take things common from here, I'll get From here, I can take x square, and I'm assuming this will be 1 plus x 3k minus 2. And this will be, if I'll take x square common from here, I'll get x square plus x to the power 2k minus 2. So these two things will get cancelled. I'll be left with this thing. Now if I'll take k is equals to, let's take k is equals to 1 first. So for k is equals to 1, the value is 3 minus 2. So it will be 1 plus x by, and this is 1, right? So 2k minus 2, this will just be 0. This will be x square. What's the limit of this when x tends to 0? This is infinity, right? So from this one, you will get infinity. And for k is equals to, let's take 2, the value will be, this is 6 minus 2, 4. So this will be 1 plus x to the power 4. And here you will have 2. So 2, 4 minus 2 is 2. This will be 1 plus x square. Now when I'll have x tending to 0, what's this limit? This is 1, right? So that means this I did for you to see that for different values of k, just
Ma'am,
like
it
this
will be
one,
2x square.
where,
X
where?
square plus x square, not 1. There was one x square,
Okay,
na?
okay, okay. So this will be 2x square. Okay, then it will be,
Again infinity.
then also this limit is going to be infinity, right? Okay. This, let's take k, let's take k is equals to half and see what happens. Does it, can we think of something else that gives us some different value? If I'll take 2 by 3 here, k is equals to 2 by 3, I'll get this to be 0. And if I'll take 2 by 3 here, I'll get, this will give me 1 plus x to the power 0. This is just 1. And this will be x square. So we're taking x square plus, okay, let's take 2 common, x square common from here. I'll get 1 and I'll get 4 here, x square. And here also I'm taking x square common. So this will be, I don't think this example works, but a lot of examples are there that do work in this manner, where for different values of k, you get different values for the limit.
And can't we take k equal to 0?
K equals to 0. If we'll take, yeah, you can do that. No, no, you can't take k equals to 0. That will give you y. If you have y is equals to x to the power k, if you will take k equals to 0, that means y is equals to 1, right? And y is equals to 1 curve is this. Y is equals to 1 is this, and this does not pass through 0, 0, right? So you can't take 1. I've already mentioned this thing that k has to be greater than 0, haven't I? I think I've mentioned it somewhere that k has a restriction on it. It has to be greater than 0. Maybe this example is not working for this particular k case, but for different values of k in this one, what happens is for different values, like in this one, for different values of m, you're getting different values of the limit, right? That's why limit does not exist. Similarly, in some cases, for different values of k, you get different values of,
Limit.
yeah, you get different values of limit. I think this should have worked. If I take y is equals to x, I'll get, what happens if I'll take y is equals to x, I'll get x square plus x cube. And if this will be x4 plus x square. So if I'll take x square common from here, I'll get x square plus 1. And here I'll get 1 plus x. And when x tends to 0, this gives you 1, right? What did we do here then? If I'll take x square, this was x square. This was plus y. So y is x to the power k. So I'll get x to the power 3k. divided by x to the power 4 plus x to the power 2k. And if I'll take square common from both, I'll get 1x 1 plus x to the power 3k minus 2. And here I'll get x square. So I'll get x square plus x 2k minus 2, right?
Right.
If I'll put k equals to 1, I'll get 1 plus x and just 1 second. For k equals to 1, this becomes 1, right? So this will be 1 plus x and x square plus this will be 0. So this is x square plus 1. Yeah, so this should be 1, right?
Right.
This limit will be 1. And this limit is something else. So via different values of k, you're getting different value of the limit. This implies limit does not exist. We'll do one last example and then we'll end this here. Okay, before that, I'll discuss the definition of continuity. It's nothing more than what we've already discussed. So continuity is basically when your limit of a function, and I'm discussing all kind of functions here, multivariable, single variable, all kind, because we've discussed all kind of functions. So if limit of fx is equals to, as x tends to a tilde, let's take tilde here, is equals to f a tilde. If this happens, that means your function is f is continuous. This is the definition of a continuous function. If your limit, if limit of this function f is continuous at a. So if you need to check the continuity at a given point a tilde, then you just have to check whether the limit of this function at a tilde is equal to its value or not at a tilde. Value of the function at a tilde and limit of the function at a tilde. That's what you have to check. So let's do one example. Let's say you have fxy is equals to x square y by x square plus y square. And here you have, let's say, 1. And you have to check whether this is continuous or not. Do you think this is continuous? Let's see. First, we'll discuss the limit of this. Limit when xy, this is when xy is, this is obvious, but I'll still write this. This is when xy is 0, 0. At the point 0, 0, because this function is not defined at the point 0, 0. So this is the value we are taking is to be 1 at 0, 0. So is this continuous? For this, we'll first need the limit. What is the limit? And does the limit exist at all in the first place? If you have this function, then this, let's have a closer look at x square y, what our function is, x square y by x square plus y square. And this is, let's take the mod of this, and this is greater than 0, right? This mod, this function's mod is greater than 0. And can I say, because if I'm moving close to, let's say, not even close to, let's say if I'll remove y with a 1, or let's say if I'll remove x square with a 1, this one, if instead of this x square, if I'll do 1 here, if I'll have y by x square plus y square here, can I say this is less than this? Why we're doing this is because we're trying to use the sandwich principle. Trying to use sandwich principle, which says that if your function is sandwiched between two functions, where the limit of both of the end functions is the same, then the function of this should be same, right? So we're trying to sandwich it between two functions. Now 0 is a function, it's a constant function, and this is also a function. And why this thing is, if I have in general x square y, this denominator I've kept constant, right? I've kept the same, right? We're only talking about the numerator. We have changed the numerator, and I'm saying the mod of x square y should be less than mod of y. And why do I say so? Because x square is, not to forget that I am taking the case when my x is coming close to 0. So when my x is coming close to 0, that means I can take x to be less than 1, can I? Because if I'm saying that my x is going
Yeah,
close to
ma'am.
0, then eventually it has to be less than 1. Otherwise, it can't approach to 0, right? So the case
Yeah,
that
ma'am.
matters is whenever you have, and this is a point that I want you people to understand, that whenever you have something tending to some point A, then the tail matters. That means if you have x1, x2, and so on till xk, and so on, then even if I'll remove first k terms or first crore terms, it doesn't matter, right? Because we're only interested in what's happening eventually. We are interested in the eventual behavior. Similarly, if I say x is coming closer to 0, then I'm only interested in the eventual behavior. If there is a sequence that's converging to 0, if I say xn is converging to 0, that means this sequence is eventually less than 1, right? This is x1, x2, and so on, xn, and then so on. If this has to go to 0, then after a certain point, it has to be less than 1. Otherwise, how will it come close to 0 if it's not less than 1? And it cannot come to close to 0 from the negative side because we've already taken mod here, right? So, and even if that's happening, it's x squared. So it's obviously positive number. A positive, that means a positive sequence converging to 0. It has to be at some point, be less than 1 to be able to come close to 0, right? So that's why you can take instead of x square, because when xy move to 0, 0, this is what you have to look for. We are considering this expression under the assumption, under the criteria that my xy is coming close to 0. So I'm only interested in the neighborhood of 0, right? What's happening around 0, 0. I'm not interested anywhere else. When I'm sufficiently close to 0, 0, when I'm very close to 0, 0, if this is the point 0, 0, when I come very close to this point 0, 0, what happens there is what I'm interested in, right? I don't want to know what's happening elsewhere. So when my xy is very close to 0, 0, when xy is close to 0, 0, or I can say in simple words, I can say when xy both are between 0 and 1, right? When this happens, then can I not say that x square is just less than 1, right? If x is less than 1, because that's what I'm interested in, then x square is also less than 1. So x square y mod is also less than mod y, because x is converging to 0. This implies x is less than 1 eventually.
Yeah, ma'am, we could also say na, that because x is greater than, I mean, approaching to 0, we could say that the value of x can be epsilon. So automatically, when we
I
cancel
don't,
it,
yeah, you can say that,
so
but I don't want to get into epsilon delta detail. That's why I've used this thing. That's also fine.
okay, ma'am, I got
Okay.
it.
So this thing will be less, x square y will be less than mod of y. That means your x square y by x square plus y square mod will be less than equals to y by x square plus y square mod. Okay. And where is this thing going now? Now, if I see this thing, or in fact, and what happens to this one? If I am sufficiently close to 0, 0, if I say x is less than, let's not even take this. If x and y very close to 0, 0, that means x square plus y square is close to 0, right?
Right.
So that means this value is very small. So I can just simply replace this Okay, if I'll replace this with a larger value, then this will become smaller, right?
Mm.
I'll have to replace this with a smaller value.
Okay.
Okay. And this can be made as small as possible, so that's not possible. I don't think this will work here. Okay, so just 1 second. We had x square y by x square plus y square. Okay, let's see this thing. All right. If I have this thing by, can I say that this thing is less than x square y plus y cube? Can I say this? I've kept the
Yeah,
denominator
ma'am.
same, but I've changed the numerator. I've added something here, right?
Yeah, we can.
We have done this because I've taken x square y, and x square y is obviously less than equals to x square y plus y cube, right? I've added something here. And in fact, the if because
Ma'am,
this y
given that
this
y
y
is
cube should
positive.
be, yeah, in case y is positive, that's when this is true. So, or we can do this thing x, just 1 second. That's fine. You can take y square here, but then we won't have x square y here. Good. Yeah, for the case when y is greater than 0, let's take y greater than 0. This is this is getting complicated, right? We have changed this numerator to this for y greater than 0. This thing should be true, right? And then we'll have this thing less than equal to, because this is just x square plus y square times y, and this is x square plus y square with a mod, right? So these two things are equal, not even less than equal to, they're equal. And then these two things get cancelled. So I'll just have mod of y. So that means this entire thing, when y is greater than 0, this thing is equal to mod of y. Y tends to 0. So the limit will be 0. So from this way, your limit is coming to be 0. Now, if I can show for y greater than 0, y less than 0, the limit is again 0, then it's done, right? Or you don't even have to go there. Just 1 second. Yeah, we don't need that. If I have y greater than 0, this limit is 0, this limit is also 0. So by sandwich principle, the limit of this thing should be 0. That's one thing. That means when your y is greater than equals to 0, fxy, limit of fxy as xy tends to 0, 0 is 0. Then we'll only have to check the case when y is less than equals to 0. If it's true in this case also, then the limit is 0, right? Because we've used both cases. Greater than 0, less than 0. That means all cases have been covered. So this will give you, I don't think you will have something this complicated in exams, but let's still do this. This is for y. Can we do something for y less than 0?
And then you have to take
Or
y square.
that's of no use. If I'll take y square, I won't. I'll have to multiply this with y square. That's
Yeah, yeah, ma'am.
okay. That's fine. But we just know that the limit of this function, what does this mean? Let's just end it here because we'll have to check a lot of other things as well for this question. We'll have to come up with something for y less than equals to 0 case. But I know that if I'm approaching 0 point from y greater than 0, that means if there is any curve from this side, y greater than 0 is this side, right? This is y greater than 0 side. That means if I have any curve approaching to 0 point from y is equals y greater than equals to 0 side, that via that curve my limit will be 0, right? From the negative side, I can have some other limit that we haven't checked yet. But from the positive side, we are sure that any curve that approaches to 0 from the positive side would give you 0 limit. Is that okay?
Yeah, ma'am.
And if in particular, okay. Anyway, if you're getting limit 0 here from one of the curves, that means from one of the curves you're getting limit 0. And this function's value at 0 is 1. That means even if the limit exists, it will have to be 0, right? Because via one way, we have found that the limit is 0. Now, there are only two cases. This is when y is greater than 0, greater than equals to 0. Limit of f is equals to 0. Now, there are two cases. Either for y less than equals to 0, limit is equals to 0. That means limit exists, right? And is equals to 1. Sorry, 0. And the other case will be for y less than equals to 0, limit is different or does not exist, right? Let's say limit is different, limit is not equals to 0. This implies limit does not exist. Now, if limit does not exist, that means the function is not continuous. If you can't find limit, then how can you say that the limit is, then we can't even say that the limit is equals to function's value, right? Right. So that means the function is not, in this case, function is not continuous at 0 does not exist at, this is all about 0 point at 0 point. And if my limit exists and is equal to 0, even if that happens, my limit exists and it's equal to 0, but my function's value at 0 is 1. That means but f of 0 is equals to 1. This implies f is not continuous at 0. Is that okay? So for continuity part, it's very clear that the function is not continuous, but for the limit part, we'll have to see how to solve this. Is that okay? Does anyone have a doubt in anything? Can we end this session here? Otherwise, does anyone have any doubt? Okay, so we'll end this session here then.
Okay, thank you.